Hello, we're Team 0 Degrees, and our project is finding quiet cooling alternatives to the lithography machine's nano-precise scanning stage. At the heart of all our smart devices is a processor chip comprised of billions of tiny structures made of semiconductors like silicon. The process of turning silica sand into a packaged chip is a long, resource-intensive process, and lithography, the step where these nanometer-scale structures are engraved, is the most energy-intensive of them all. ASML, this project sponsor, accomplishes this using high-energy ultraviolet light reflected off a nano-precise pattern held in a moving reticle stage in their most advanced lithography machine. Any thermal expansion or dynamic vibration can cause defective semiconductors, wasting time, energy, and material for manufacturers. Team 0 Degrees has the objective to explore and prove methods to maintain the reticle at a constant, controlled temperature with minimum vibrations. EUV lithography machines are solely produced by ASML and cost upwards of $150 million each for their main clients, who are large chip manufacturers like TSMC, Samsung, and Intel. As such, only a couple dozen machines are rolled out in any given year, but each machine can expose thousands of wafers of chips each day. As such, even small percentage improvements to the system can lead to drastic benefits for ASML, their clients, and the end user. The reticle stage of the lithography machine oscillates linearly along a track, and ASML's current solution uses water channels to cool the stage. Our design prioritizes minimizing distortion through passive phase change, since a passive device reduces the amount of dynamic linking to other objects in the system. Reduced operating pressure also reduces mechanical deformation. And unlike normal liquid, which rises in temperature as it picks up heat, fluid undergoing phase change will maintain a constant temperature throughout, keeping the entire length of the channel at the same uniform temperature. Our design, a hybrid heat pipe and thermosiphon array, will sit within the internals of the stage. Heat pipes are passive devices which operate in a self-contained cyclic motion of liquid and vapor. A wick is included to help the liquid spread along the length of the heat pipe. As heat from the target body transfers to the walls of the heat pipe, heat is picked up by the liquid and it evaporates. The vapor travels up the thermosiphons towards a condenser, where the heat is rejected and, like rain, it falls towards the pipe as liquid to be cycled again. The temperature at which phase change occurs can be manipulated by changing the internal pressure of the system, allowing for precise tuning of the operating conditions. There are limits to how much heat a given heat pipe can disperse, but our design can meet not only the current demands of ASML, but also their future aspirations as they continue developing their machines. Our experimental setup successfully models the desired behavior by maintaining the heat pipe exterior at a steady, uniform temperature. Our prototype also models what the system would look like should it be installed into ASML's machines. We estimate that our system can reduce the thermal distortion of the reticle by 194 picometers, or 1/36,000th of the diameter of a single red blood cell. Keep in mind that this number does not account for any additional benefits of not dynamically linking the system to a pump. This value may seem insignificant, but even tiny improvements on the scale of 10 to 20 picometers can increase chip yield by 1 to 5%. For factories producing thousands of wafers of chips on each machine every day, the savings reach tens of millions annually. With less deformation, smaller-sized features can be pushed, and more chips can be manufactured for the same dosage of energy, making the entire process more efficient. Less waste from defective chips will help conserve resources and reduce the industry's carbon footprint. Lastly, end users all over the world, like us and you, have better access to cheaper, more efficient, and more powerful devices, including phones, medical devices, cars, computers, and more. Thank you for watching.